Hello again, everybody. All right, go for round 2 here. And first off, I'd like to apologize because I did make some egregious mistakes when it came to some of the oscilloscope use in the last one. But you know, if I didn't make mistakes, I wouldn't learn anything. And I want to thank the people that pointed out some flaws and took the time to give me a little bit of helpful advice. That is most appreciated, and that certainly is what, you know, progresses our society in general. But without getting too esoteric here, so across the positive is our channel 1, okay, and across the resistor is our channel 2. So we can measure our voltage drop and do some calculations. And I took an average basically of about 80.6. It really dances around a lot, but it's kind of the best I came up to. And you can see the inefficiencies of the reed switch, whether it be the positioning of the magnets themselves, or just the reed switch opening more and less depending on its pass around, the magnetic field pass around, or, you know, affecting the reed switch. You can see it really does affect the current, or the current is the total general of the volts and the amperes, but the amps, it affects the amps for the most part. So there we go. You can kind of see how it changes. Amount of joules delivered in a certain amount of time, right? So, or amps delivered. But you can see some of these kickback peaks, which is really cool. And if you are curious about the AC waveforms that are coming from the interaction between the phases, you can look at the last video. I have some decent scope shots of some of the AC waveforms. So let's do some of the math here. We have 85.8 to the second divided by 150, which is our ohms of resistance, and we get 49.076 milliwatts, or if we round up, we'll get 49.8 milliwatts, with 0.572 milliamps, just to cross-reference to make sure that that's correct. Now that's the RMS value, so this is being able to capture the AC pulses, the back spiking, and all that kind of fancy stuff. But the averages comes up with a little bit of different value, which is a little less. But this is not necessarily what you want to use. I just did it to kind of get the average between the two, and also just for some more measurements and stuff like that. So now I'll show you a couple. Alright, this is for Jeremy. I believe there's 18 sections here, but let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yeah. So there's 18 laminated core sections, and they all share, it looks like they all share a magnet, though it's isolated with a piece of plastic, so my guess is so it doesn't ground to the chassis or the housing. They all share magnetic flux, or magnetic field lines of force, in the laminated cores. So it's pretty impressive, something that I probably couldn't machine or create myself, but it's pretty cool. And the gauge wire looks to be about 18 AWG. It might be larger than that. I'm not quite sure. I can't be solid on it. That's just a guesstimation. But figured I would do that. Three phases. Oh, and has ceramic magnets that are would it be diametrically opposed, so they go along the radius of the actual cylinder. They go north south per each magnet, and there's 4 magnets, so that makes 4 norths and 4 souths, 8 magnet positions altogether. I'm pretty sure that that's how they're set up, but I could be, because I couldn't see why they would do it polarized, or not polarized. What do you call the other? Axially. I couldn't see why they'd be axially. I think that's correct. The correct terminology, where it's on either side, because then it would just be stuck to this interlaminated rotor. And what's interesting is actually, like, I'm kind of curious what's behind this rotor and how it's affecting the lines of force. You know, like if this is a laminated rotor inside of there too, like an induction, like a standard induction motor. That's also very interesting to think about, and how all the coils could kick back with each other. It's kind of cool. It's a very cool motor. So that's the inside. Let's move on. Alright, this is kind of a cool demonstration that I wanted to get into some of this stuff. One is, right now I'm measuring our pulses into the capacitor. So not the raise of the capacitor per se, just what's hitting the capacitor itself onto the positive side. And I've rectified it between the two phases using what came in the module, this X13 module, and then I have it in this capacitor. Now, capacitor as well. It's a 1,000 volt. It's a 1,000 volt or 1,200 volt, 1,000 microfarad capacitor, and I basically just have it, instead of running in between the neon and this inductor, I have it rectified between those two phases, and then I'm pulling off the DC. So it's capturing the AC and the DC and just rectifying what's coming, the back spiking coming out of the motor. And if you look here, yeah, pop's not so great, right? You know, there's some spiking there, but it's not fantastic. See, I mean, considering. And now watch what happens when I ground the negative side. Just ground it for a bit, right? Pop got a little bigger. Now watch what happens when I ground it for a little longer. I could wait for the buildup on this too without the grounding. It's just not quite the same. It's, see that pop? Much larger. Now we'll wait the same kind of duration here. Okay. It's probably been a little longer even, right? Look at that. Pop's just not the same. So what we can do is, let me see here. Why don't we go like this? We'll try this. We're going to take the battery ground, or we're going to take the an earth ground. All right. And we'll take another ground and see if pop will be substantial again. Then we'll start looking at some ways maybe to bridge that, maybe halfway, or just a blocking diode so it goes back to our battery source. Whew, that was a pop, and I didn't get it in camera, but that was pretty nice. Let's go back to this here. So now all the grounds are connected. There's no action happening here. Now I don't want to pop it with the scope on, not because I'm so worried about destroying the oscilloscope in general, but the actual probe. I don't want the probe to get arced too. So, but I will go to some scope shots of this. See, quite a pop. Makes the motor stop, obviously. Okay, so now I don't mind the alligator clips getting a little bit toasted, but okay, there we go. So now we'll watch the rise on here. So it's already reached 13 volt rise, so we'll pop it out. Wow, I should have got a picture of that one. And then we'll go to the rise. Channel 2 obviously is on across the across the capacitor. So they're both are in the same position. You can see it goes to about 13 volts, and you can see it climbing here as an average. And there we're at 13. All right. So now I'll take this off and try to hit it to where I don't get the ground channel. Whew, that was juicy. All right, so that's another little demonstration that I know that Terry will be interested in. So I figured I'd give some scope shots of that, and for everybody else. So there's that. Now I got one more thing to do, so as requested Jeremy. So hold on. All right, this is kind of a silly little thing. This is a hint at a pulse motor build off too, in a way, but I don't know the approximate weight of that battery. I know the approximate weight is probably somewhere around 8 to 10 pounds, but I don't know the exact weight. That'd just be a guesstimation. There's our channel 2 is our again across the resistor. You can see our drop, and now we have the measurements for that, but I'd have to get the proper weight, you know, for the mechanical load. And also this mechanical load is horizontally positioned, which is a whole other series of equations that I have yet to completely delve into or use, and you know, problems I should say is if the axis of rotation is horizontally configured or like this is, or vertically configured, how that changes efficiencies and stuff like that. That's kind of a, I should probably Google that, see if somebody's actually done that. It'd be a good experiment to understand. But what else was I gonna go over? I think that's pretty much it. Yeah, that's pretty much it. I'll get more details into this later, but I can't mess with this with the X13 too much more. So a third video probably won't come for a while. But hopefully, if there's anything I made mistakes on, or anybody wants certain readings, I'll have it set up for a couple more days just to see if anybody wants to throw in their 2 cents, or bring up a flaw that I have, which I'm sure there's got to be a couple in there somewhere. And again, this is channel 2's on 1 volt divisions. Channel 1's 5 volts. Our math is at 10 volt divisions. And we're multiplying channel 1 by channel 2. And yeah, we can also see what our drop is too by going like this, I believe. Subtract channel 1 from channel 2, so we can see our like an AC sinusoid. It's kind of weird, probably because it's also switching through the transistor at the same time. If that reed switch, when that reed switch fires, it also oscillates through the transistor circuit too. So, anyways, cool stuff, and look forward to more to come for the people out there, and cheers.